Welcome to the deep dive. We're digging into this fascinating material you shared, lecture notes, briefings, study guides, all pointing towards something really core in AI.
Yeah, it's about that fundamental link between an AI agent and, well, the world it actually operates in.
Exactly. So our goal today is to really pull out the key takeaways. We want to understand how this external context shapes AI, the tools used to define it, and, the challenges these environments present.
Because understanding that world is, like, the absolute first step. It underpins everything else.
Okay, let's jump right in. The sources are really clear on this. And AI success isn't just its internal programming, it's, and I'm quoting here, profoundly shaped by the external context in which it operates.
And that context has a name in AI circles.
Yeah.
The task environment. It's basically the specific problem or set of problems the AI is supposed to solve.
And getting this definition right from the start is, well, it sounds critical. The materials say it's the foundational first step in the entire AI agent design process, like non-negotiable.
Absolutely non-negotiable.
Yeah.
Because if you get it wrong, if it's vague or just incorrect,
Then what happens?
then you inevitably build an ill-suited or ineffective agent. You've basically shot yourself in the foot before you even begin. The whole project is compromised.
Okay, so step one, absolutely vital. How do we actually define this world in a structured way? That's where PEAS comes in, right? This framework.
That's the one, PEAS. It's pretty widely adopted, developed by Stuart Russell and Peter Norvig, back in the early 90s, I think, around 93. It gives you a blueprint.
Right. PEAS. Let's break that down. P is for performance measure.
Yeah, performance measure. How do you score the agent? How do you know if it's doing a good job? It needs to be objective, clear, and ideally something you can actually measure.
Like what kind of measures are we talking about?
Well, it really depends on the task, you know?
Yeah.
Could be maximizing profit for a trading bot, enhancing efficiency in a factory setting, improving accuracy for medical AI.
Or even things like ensuring safety, customer satisfaction, minimizing time.
Exactly. Or providing comfort, like in an autonomous vehicle. The point is, a well-defined measure ensures the AI focuses on what truly matters for success. Without it, it might optimize for something else entirely.
Got it. Okay, P is performance. E is environment.
The world itself, everything outside the agent that it interacts with, conditions, other entities, the whole playground.
Simple enough. Then A, actuators.
Actuators. These are the agent's hands, its voice, its way of acting on the environment. They turn decisions into actions.
So for a robot, that might be robotic arms, wheels, motors.
Right. Physical stuff.
Yeah.
But for software agents, it could be displaying something on a screen, sending an email, changing data in a database. They need to be reliable, precise.
Yeah.
You get the idea.
And finally, S is for sensors, how the agent perceives things.
Exactly. It's eyes and ears. Sensors provide the raw data about the environment. They're the interface to the world.
So cameras, microphones, GPS, LiDAR for physical agents.
Or API feeds, user inputs, keyboard entries for software ones. They gather the info the agent needs to make smart decisions.
Okay, P's. Performance, environment, actuators, sensors. But it's not just a checklist, is it? The sources stress how interconnected these are.
Deeply interconnected. That's the key insight. Think about the automated taxi example they used.
Right. If the performance measure, P, is passenger comfort,
Then the environment E isn't just roads, it's roads with bumps, traffic jams, maybe even weather.
which means your sensors, S, need to detect those bumps, predict traffic.
Precisely. And your actuators, A, the steering, acceleration, braking, need to be super smooth. Now change that P to get there fastest.
And everything changes. Maybe you need different sensors focused on traffic prediction, more aggressive actuators. The whole setup shifts.
You see it everywhere. Medical diagnosis. P is health accuracy. E is patient data knowledge. A is display disorders. S is symptoms results. Part picking robot. P is speed no damage. E is conveyor parts. A is the arm. S is vision touch.
Even a spam filter. P is accuracy, E is the inbox mails, A is marking spam, S is content sender infos or actions. It really forces you to think systemically.
Exactly.
Yeah.
P's defines the what. But then there's the how complex is it? Not all environments are the same. Their properties dictate the kind of agent you need.
This is where the classifications come in, like observability, fully observable versus partially observable.
Yeah. Fully observable means the agent sees everything relevant. Simpler design. But partial observability is more common in the real world, hidden info, uncertainty.
So what does the agent do then, if it can't see everything?
It has to infer. It needs internal memory, maybe a world model, to kind of guess or estimate the hidden state based on what it can see and what it remembers.
Okay. Then there's agent count, Single agent or multi-agent?
Are you alone or are there others? Solitaire versus poker, basically. Multi-agent settings bring in cooperation, competition, strategy, whole new ballgame.
Makes sense. And predictability seems huge. Deterministic, stochastic, strategic.
Deterministic is easy. Action A always leads to outcome B. Predictable. Stochastic means there's randomness, like rolling dice. New probabilities.
But strategic is different from just random.
Yes. Strategic unpredictability comes from other agents making choices. Think chess opponent, not just a random event. It requires reasoning about others' goals and actions.
Right. Then temporality. Episodic versus sequential.
Episodic means each decision is self-contained, like classifying one image. Sequential means actions have ripple effects over time. Your move now impacts the game later. Needs planning, memory.
Immutability. Does the world change while the agent is thinking? Static dynamic, semi-dynamic.
Static means no change, while deliberating the agent can take its time. Dynamic means it does change. The agent needs to be fast, maybe interrupt itself. Semi-dynamic is a weird middle ground where the environment is static, but your score might change, like a time penalty ticking down.
Okay, almost there.
Yeah.
State action space, discrete versus continuous.
Discrete means finite options like squares on a board or menu choices. Continuous means values on a spectrum like steering angle, temperature, speed.
And continuous spaces can get really complex, right? The curse of dimensionality.
Oh yeah. When you have many continuous dimensions, the space of possibilities just explodes. Makes it incredibly hard to explore or learn effectively.
Last one, knowledge. Known versus unknown environment rules.
Known means the agent understands the physics or rules beforehand. You can hard-code models. Unknown means it has to learn the rules by interacting, by trial and error.
Which leads to that whole exploration versus exploitation thing. Trying new stuff versus sticking with what works.
Exactly. That's a classic challenge for learning agents in unknown environments. So you see, piling these properties up, partially observable, multi-agent, dynamic, sequential, continuous, unknown, that's where AI gets really challenging.
Definitely. And the agent navigates all this complexity using perception and action. We touched on them, but let's revisit quickly.
Sure. Perception is gathering and interpreting sensor data, how the AI sees or feels the world. It can be physical sensors, software inputs, even virtual simulated data for training.
But it's not perfect. There's noise, ambiguity, maybe just too much information.
Right. That links back to partial observability. The agent has to process that raw, messy input, filter it, make sense of it.
And on the flip side, action. Using actuators to influence the world.
Physical limbs, software commands, virtual actions and simulations. The challenges here are things like executing actions precisely, managing resources, and, this is important, actuator environment matching.
Impedance matching, they called it.
Yeah, basically making sure your tools fit the job. Don't use tweezers for boulders or a sledgehammer for watch repair. The actuator needs to be suited to the task and the environment otherwise.
Catastrophic failure.
Could be. At least very ineffective.
So you've got perception feeding into decisions, decisions feeding into actions, and actions changing the world, which then changes perception. It's a loop.
The perception action cycle, that's the absolute core loop. It's continuous. Perceive, process, decide, act, environment changes, new perception, and round it goes.
And this cycle isn't just mechanical. The sources say it's where intelligence is embodied and situated.
Exactly. It's how the agent is dynamically coupled to its world. Intelligence isn't just thinking. It's expressed, tested, and refined through that ongoing interaction. It's a deeper understanding the agent and its environment.
Okay, let's ground this. The business examples really bring it home. Take the personalized financial advisor.
Okay, let's map it. Partially observable.
Yeah.
Definitely. Stochastic. Oh yeah. Markets. Dynamic, constantly changing, sequential. Big-time decisions have long-term impact. Multi-agent, you bet. Continuous state space. Prices, values, yeah.
So a simple rule-based system isn't going to cut it. You need complex modeling, risk management, learning.
Absolutely. Or retail inventory management. Partially observable supply chains, stochastic demand, dynamic trends, sequential stocking effects. Probably a mix of continuous discrete states, multi-agent competitors, suppliers, customers.
Needs forecasting, optimization, real-time reaction.
And procurement contract negotiation. Partially observable, stochastic, and strategic, other negotiators. Dynamic markets, sequential impact, multi-agent, often partially unknown rules or opponent strategies.
Whew. That needs sophisticated negotiation, AI, market understanding, learning. What the material really stresses here is that building good business AI needs deep domain knowledge of that specific business world.
You need that domain expertise to even define the P's correctly and classify the environment. It's a critical third-order consideration, just as important as the AI tech itself.
Looking even broader, this idea that you have to tailor the agent to the environment, it connects to that no free lunch theorem.
It does. That theorem basically says there's no single best algorithm for all problems. You have to specialize based on the specific task environment. It reinforces this whole discussion.
And in multi-agent systems, it gets even wilder with the co-evolutionary dynamic.
Yeah.
Agents don't just react, they change the environment itself.
Right. Think high-frequency trading bots. Their collective actions change market behavior. Or recommendation algorithms changing what people watch or buy, which then changes the data the algorithms see. The agents and the environment shape each other over time.
So, wrapping this all up, the absolute core message from all this material is, you got to start with the world.
Yep. Understand the agent's world deeply. Define that task environment rigorously using P's. And really appreciate how its properties, observability, predictability, dynamism, etc., dictate the challenges and the kind of AI you need.
Okay, so for you listening, here's something to chew on. Think about a system you deal with daily, maybe city traffic, your social media feed, even in online games AI opponents. Try mapping its P's. What's the goal? The environment, the sensors and actuators.
And then think about its properties. Is it observable, stochastic, dynamic, sequential? What makes it tricky for an AI to navigate? And here's the kicker. How might the actions of all the agents in that system, maybe including you, actually be changing that environment over time?
It's a really interesting lens to view the complex systems around us. Thanks for joining us for this deep dive today.